thank you for tuning in to Connections and Directions, our University of Michigan Civil and Environmental Engineering podcast. My name is Michelle Santillan, and I am the CEE Marketing Communications Specialist and host of this series. During our podcasts, we are featuring members of our CEE community and how their work reflects our mission of engineers in service to society. We will be highlighting our strategic directions and our commitment to diversity, equity, and inclusion. CEE's 5 strategic directions are human habitat experience, shaping resource flows, adaptation, automation, and smart infrastructure finance. Our guest for this podcast is Associate Professor Jeremy Bricker. Professor Bricker has a Bachelor of Science degree in Mechanical and Aerospace Engineering and a BA in Physics from Rutgers University, and a master's degree and a PhD in Civil and Environmental Engineering from Stanford University. Professor Bricker and his students use hydraulic laboratory experiments, numerical simulations, and post-disaster field surveys to investigate the resilience of structures and infrastructure exposed to both increasing hazards due to climate change and increasing consequences due to expansion of development in coastal and flood-prone areas. His research focuses on 4 main themes: damage, flood phenomena, countermeasures, and hydropower. Professor Bricker, thank you for joining us today.
Thank you for the introduction, Michelle.
Please share with our listeners some details about your research area and goals and how they align with CEE's strategic directions and our mission of engineers in service to society.
Well, among the strategic directions, the human habitat experience and adaptation naturally fit the work that I do. Much of my work focuses on how structures respond to flood loading and wave loading due to hurricanes, tsunamis, or floods, river floods. And that means as the climate changes, as sea levels rise, as storms and storm intensities and frequencies change, structures will need to change as well in order to be more resistant to the forcing they're exposed to. That's adaptation. That's one method of adaptation. Other methods of adaptation are changes in land use, redefining where the built environment exists versus what to restore to a natural environment. That crosses over with the human habitat experience, where the spatial planning of a city, for example, is one method that can be used to reduce exposure to coastal hazards. This is a common method used in Japan, for example, after the tsunami in 2011, the use of coastal areas for agricultural and recreational purposes instead of residential and commercial purposes is one of the measures put in place to try to reduce vulnerability of people to the tsunami hazard. As we in the U.S. adapt to changing flood and hurricane hazards, those are lessons that we can learn from what's being done elsewhere, and that land use affects where people live and therefore the human habitat experience.
Given what you just said about, the flooding and things like that and land use and lessons we can learn, for example, the recent floods in Kentucky, is there anything specific that might be able to be put into place to avoid such devastation in the future?
Well, I think the floods in Kentucky are one example of how the classical way of determining what flood return periods are is needs to be updated in light of climate change. We determine 100-year floods, 500-year floods based on long historical data series. As the climate changes, those data are no longer stationary, and what was a 100-year flood in some cases can now be a 50 or 25-year flood. It changes, and so one way to adapt to the changing climate is to redefine where these floodplains are. If we're going to continue as we currently do with the FEMA National Flood Insurance program definitions of the 100-year and 500-year floodplains, we need to update those for what the current and projected climates are going to mean those floodplains are going to be. The other thing we can do is to consider countermeasures, such as how close we live to the rivers, such as what elevations we live at, or if we need to live in close proximity and at low elevations, the use of protective structures like dikes, flood walls, though that those themselves introduce a whole other range of hazards, such as a false sense of security, because structures themselves can fail. They're always designed to a certain reliability, and that's one of the items of research and debate within the natural hazards community is, should we build more and better protective structures to protect people living in vulnerable areas, or do these structures just encourage people to live in the vulnerable areas, and should we rather rely more on land use planning and education rather than engineering measures to reduce vulnerability? Of course, the answer is going to be some combination of the two.
Yeah, because when you go to a coastal region, for example, you see houses built on stilts, and you see people building right along the beaches, and you can only imagine how erosion can affect that, especially if a terrible hurricane comes in. A strong enough hurricane, of course, can devastate that area. Is there any recommendation for that type of a scenario on a beach, for example, or would those parameters pretty much be the same, but just using the types of regulation or education, as you mentioned, advise people not to build so closely, that sort of thing?
Well, what we can advise people to do is not always going to be what they do, right? Because there's a trade-off between building a resilient or a safe community versus one that people actually like living in. And people like to live close to the sea because it's beautiful, convenient, refreshing. I think people will always want to live near the sea. And so and this is another of the debates within the hazard and the natural hazards community is, do we want to build or to encourage people to build safely, which means in areas that are not so exposed to the hazards, further inland, further uphill, or do we want them to build where they want to live, but in a very robust way? So back during, I think it was Hurricane Irma or Michael, I can't remember, in Mexico Beach, Florida, there was an example of a reinforced concrete home on stilts on the beach amongst all the homes made of timber, also on stilts on the beach, where the really solidly built reinforced concrete home was not destroyed, whereas the ones around it were. That's an example of, if we're going to build in the hazard zone, an expensive but reliable way to reduce the vulnerability of structures there. But even those structures will have their limits. There's always going to be an event that's going to be above the design event for any structure. So for most of the events, most of the hurricanes that we foresee, a structure like that might be great to have, but for the largest events, it also will fail. So even with structures like that, if we're going to live in a hazardous area, education is still the most effective countermeasure to make sure people know when and where to evacuate. Mm-hmm. I think that's one of the measures that the United States is really well renowned for, is the encouragement of evacuation from hurricanes and the great response to that encouragement. In Japan and the Netherlands, which are other countries with strong hazards, storm surge hazard, tsunami hazard, people have tended to feel a false sense of security, protection, by the structures in place to protect them, the dikes, the seawalls. But in events that were larger than the design they were designed for, they have failed. In the case of the U.S., where we don't have a lot of protective infrastructure, people know they have to evacuate, and they do it every year.
Mm-hmm.
So it's a strong point of the U.S. system that people do not have the full sense of security and know they have to take responsibility for themselves.
How did you become interested in your area of study? Was there a course that you took at some point or a personal experience that you had that led you to explore this topic in depth?
There are 3 items that brought me to it. One, when I was in college and I was studying mechanical engineering, I really enjoyed fluid mechanics as well as mechanics of structures. This is a natural intersection of the two, the resilience of structures against floods. When I was also in college, I was on the crew or the rowing team. We'd row past many structures we were confined by structures in the river, such as dams. And I saw many locks and gates regulating what were old shipping canals, barge canals that I thought were very interesting. So that brought me to study hydraulics. And then after graduate school, when the Hurricane Katrina happened in 2005, and in 2004 the Indian Ocean tsunami happened, the effects of these large disastrous events on structures really came to my attention as something that I was excited by understanding. Then when the tsunami happened in Japan in 2011, I had the opportunity to investigate damage to or destruction of coastal bridges and breakwaters and dikes. That set me off on my current course of research.
When you said you examined that, were you able to actually visit Japan and see that firsthand, or were you studying it from afar?
No, I went there
Okay.
to survey the bridges and breakwaters that were destroyed.
Mm-hmm.
Take measurements of scour holes, measurements of structures that were displaced, to be able to use to validate hydraulic model results that I simulated afterward.
So you were really able to learn from the past and move forward with that.
Correct. I think in this field of civil engineering related to natural hazards, that's one of the best tools that we have, because we're not able to recreate these natural hazards in the laboratory, at least at scale. So when there's a lot of data in the field that can be recorded, that can be used to validate hindcasts, which is the past version of a forecast, which is the future. Hindcasts of the disastrous events, the hurricanes, the tsunamis, to make sure we're simulating them right. And that allows us the best guess at what really happened.
Mm-hmm. So using that information, what classes are you teaching this semester? And do you have ideas for future courses you would like to one day incorporate into the CE curriculum?
This past semester, I taught design of hydraulic systems, which is about piped drinking water systems, as well as hydropower systems. Water supply systems and hydropower systems are the same thing. They just work in the opposite direction. Water supply systems use electricity to drive a pump to pressurize the system. Hydropower systems use pressure to drive a turbine to generate electricity, so they're the same things in reverse. This semester, I'll be teaching a course on tsunamis, floods, and hurricanes, which is related to my research, to help students experience what it's like to work as a practicing coastal and hydraulic engineer and design the types of structures they'll have to design in that career field. And the other course that I'll be teaching in the winter is undergraduate fluid mechanics, which is the basis of all of this.
Okay, so it gives people a good foundation then, really.
Right. Well, that together with mechanics of solids or mechanics of materials, I guess, are the real foundations to this field.
And how do you incorporate diversity, equity, and inclusion into your research and courses?
One thing that makes that easy in my field is that my simulation results are spatial. That means if I simulate a hurricane or a tsunami or a flood, it'll simulate how the inundation affects all the neighborhoods of a city, for example. So I have a current project or an upcoming project where together with a social scientist and an economist at Texas A&M, we'll be hindcasting Hurricane Ike, which hit Houston back in 2008, and simulating a bunch of hurricanes in the future to assess how the storm surge barrier that is going to be built there will differently affect different communities of different socioeconomic status. And using a model like this, we can tweak the barrier designs to differently affect different communities. And one goal, of course, is always to minimize damage. Another goal is to maximize the equity of protection. So we're not only protecting the neighborhoods that already have all the money to pay for the repairs that they need, but to also protect those who are more vulnerable. Mm-hmm. So it's a natural way, since the work itself, the research itself, the simulation results are spatial. It's straightforward to assess how proposed countermeasures, be it barriers like this, or be it retention basins, dams, beach nourishments, coastal wetlands, permeable pavements, rain gardens, how all of those will affect the spatial distribution of flood damage, which allows us to understand the equity implications of any proposed countermeasures before we actually build them.
And what is the most exciting part of your research when is it when you're doing these field assessments? Is it when you're teaching with students, or a combination of both?
The field assessments themselves are very interesting, but you got to remember they're always after really devastating events. So I can't say they're exciting. They're a combination of fascinating and horribly depressing, because you see areas and you see people at their lowest. But that being said, those people who have experienced things that they own destroyed often want to talk about it. They want people to understand what they've lost, and they want to help make things better. So even though they're grieving in many cases, they many of them want to share their stories and help improve things, which is our job. But that being said, when you are in a field like this, I've been to many places that people tell me have been just excellent vacation spots, but I've never been there for vacation. I'm always there after a disaster. Like the Gulf Coast of Mississippi, New Orleans, I've only seen when the bridges have fallen down and there are no buildings left, just foundations. Whereas people I've talked with tell me how beautiful they were and they can be again. I would love to go back and see them again when they are rebuilt and people have recovered. So the field studies are fascinating, not exciting though, because of the situation that you're in after disaster. The most exciting part of the work as an educator is to see students get it. Mm-hmm. They struggle to understand a concept, and then suddenly they're applying it correctly. That's satisfying and exciting to me as a teacher. Mm-hmm. What's exciting as an engineer is to understand what could have been done, what could be done to a structure so the destruction doesn't happen again. Mm-hmm. Like, for example, I was studying a bridge in Japan that was destroyed by the tsunami 11 years ago. It turned out that if that bridge had been built a little bit differently, meaning if the seawall hadn't been built under it, or if it hadn't been banked for the traffic on it, it wouldn't have been destroyed. Understanding the physics that caused the destruction and being able to understand, well, how could it have been designed so it wouldn't have been destroyed, or how could the next one be designed so it wouldn't be destroyed? that's what's exciting to me, is understanding what destroyed something and being able to say what should be done so that something that's going to replace it won't be destroyed in the next event.
And that really gets back to our mission of engineers in service to society, because you are preventing, hopefully, that future devastation. You are building stronger for the future, and in the process, probably saving countless lives, or at least minimizing the harm brought to people in that future weather or climate disaster.
I hope so. I like the way you state that. But I think that might be what sets civil engineers apart from other engineering disciplines, is that civil engineering is engineering in service to society. That's usually the reason people go into civil engineering. They want to do something that helps civilization or helps people, as opposed to making a better widget. They want to make people's lives better. Mm-hmm. And I think that's what defines civil engineering.
Thank you for listening to our podcast conversation. For more information about CEE at Michigan, please visit our website at cee.umich.edu. You can also reach our YouTube channel and Facebook, Twitter, Instagram, and LinkedIn pages from our website.